Okay, yeah, so I'm Dominic. Most of you know me, even those who aren't OpenCredo, as I think quite a few people here will know me from other places and contexts. I am followable on Twitter. I created a Twitter account specifically for the purpose of being visible to the outside world. So this talk is about Concursus, which is a thing I've been making for the last month or so. The subtitle is Event Sourcing for the Internet of Things. This is the only time in the entire talk I'm going to mention the Internet of Things. For present purposes, the Internet of Things basically is synonymous with IP-enabled light bulbs. So whenever you see a light bulb in the coming slides, I want you to think, yes, Internet of Things. Okay. So I'd like to start with a quote from a very interesting talk I watched a few days ago. This is from Greg Young, who invented the term CQRS. And he said, "I have told people over and over and over again, don't write a CQRS framework. I can basically guarantee you that it will be abandonware within 1 year, like every other one has become." So I felt great about that. And I then thought, well, okay, have I written a CQRS framework? Will it be abandonware within 1 year? It's an interesting question. So what is Concursus? It's an open source project. It's based on extensive research and development and implementation work we've done with multiple clients. It's not abandonware yet. It's still being actively developed. And I think it's both slightly more and slightly less than a CQRS framework. It's more like a collection of pieces you could use to make a CQRS framework if you were so inclined. It also actually allows you to explore patterns that aren't kind of strict or standard CQRS. So it's a slightly deconstructed CQRS framework. I think that's the most pretentious way I could possibly put it. Concursus is not a spell from Harry Potter. However, originally it was called Concourse, and then I discovered that there was a database and also a CI system called Concourse, and 3 concourses seemed too much, so I went for the Latinate name, again favouring pretentiousness wherever possible. So I'm going to talk about 3 things that Concursus is. First of all, it is a domain model. In other words, it's a set of answers to the question, what is an event? When I say a domain model, I don't mean that it's a model of a particular business domain, what are the events for my business, but it is a generic domain for thinking about events and event processing. It's a processing model, so how do events move through the system? Concursus kind of captures some patterns and some opinions about how event processing should be done. And it also offers a programming model. How do we work with events? How do we use our programming language, Java 8 in the first instance, to work with events in a reasonably kind of low friction way? So, light bulb. Here we have a sequence of events that might occur with a light bulb. At some point a light bulb is created, it gets screwed in somewhere, it gets switched on, it gets switched off. At some point somebody tries to switch it on and the light bulb blows, and that's the end of its life. And we can start to attach a little bit of information to this. So the light bulb has some kind of identity. It has we call these things aggregates for reasons to do with domain-driven design, which introduced the term. Everybody outside of domain-driven design says entity. It's very confusing. But we're calling them aggregates. And a light bulb obviously has an aggregate type. It's a particular sort of thing. And also it has some identity, which in this case is a unique identifier, UUID. So all of the things that happen to this light bulb happen to the entity that has this type and this ID, which is sufficient to kind of identify it everywhere. The event itself, importantly, has an event timestamp. When did this happen? It has an event name. What kind of event is it? So it's a created event. And it might carry some additional data in the form of parameters. So when the light bulb is created, we might be interested in knowing what wattage it has. It is a 60-watt bulb, a 100-watt bulb, or whatever. When it's screwed in, we have a timestamp a little bit later on, and it was screwed in somewhere. It was location hallway, for example. So events have event names, timestamps, maybe some additional data which might vary from one event to the next, and they occur to some aggregate that we can address and identify by its type and ID. Another way of looking at this is that we can look at the event history of our aggregates, which is the same set of events but just sort of ordered in a log. And the thing to notice here is that we have a second timestamp, which is a processing timestamp, which represents the time when the system observed the event and wrote it into the log. So the event timestamp is a timestamp issued ideally by the thing itself. It's as close to the source as possible. It's when the light bulb says it happened. The processing timestamp is when we say we observed that it happened, when we received the event and processed it and recorded it. Once we have a log of events that have occurred to something, we can then start asking questions about what its current state is, or what its state may have been at any given time in the past. We might model that through a kind of traditional state machine. So at the start, our light bulb doesn't even exist. It's created. Now it exists, and it's in an unscrewed state. It gets screwed in. It's now in the off state. If it's switched on, it enters the on state. If it's switched off, it goes back into the off state. Once it blows, that's its end of life, end of the state machine. So we can see events as marking transitions within a state machine model. So to know whether or not a particular light bulb was on at a particular time, we replay the sequence of events up to that time through this state machine and see where we ended up. It's on at this point. It's off at this point. We might be interested in recording all the times it was switched off and on, figure out how long it's been switched on for, and based on its wattage, make some estimate of its power consumption. Commands, I'm not going to say very much about. Essentially, the idea is that with a command, you have a request to do something like create a light bulb. You get a result back. It tells you whether you've been successful or not. And your command processor emits events that record what happened, what the outcome of the command was. So typically, the semantics are, we say something like create light bulb. It's an imperative, it's a command. And assuming we're successful, what's recorded in the system is a created event attached to the light bulb we created. So summarize the domain model. Every event occurs to an aggregate, which is identified by its type and AD. Every event has an event timestamp, which is generated by the source of the event. An event history is a log of events, ordered by the event timestamp, with an additional processing timestamp which records when the event was captured. The aggregate state of an aggregate is its state at a given time, which is determined by the event history for the aggregate up to that time. And a command is issued by a command issuer, processed by a command processor, which emits events and returns some results. Okay, on to the processing model. So we see a number of things, light bulbs again, all emitting events. And of course, the thing will emit events in the order in which it observes them occurring. Once these events hit the network, various things will happen to them. They might get routed to different event processors based on load balancing or other things. So any given processor might get events for different sources, kind of interleaved together, and they might arrive out of order. So here we can see, for example, that the terminal event of our star-emitting light bulb comes before some other event. It blew and then it was switched on. Well, that's the order in which the events arrive. The event timestamp gives the true order, but the processing timestamp may record that things come slightly out of order. So we have to take this slightly kind of jumbled or randomized sequence of things and get it into some sensible order in order to reason about what's actually happening in our system. And to do this, we need to partition our events by aggregate ID so that we have a separate log for each item, and we need to order them by event timestamp so that in the log at least they're put back into the order that the event issuer say they were emitted in. So the question is, what kind of mechanism is suitable for doing this? And one that we found very good is Cassandra. So I'm just going to talk quite quickly through this. If we imagine we have a table that simply records events. You have the aggregate type and ID. That's the partition key for the table. So that picks out an event history to write into. You then have the event timestamp and something called a stream ID, which allows us to disambiguate events for the same thing that occur at the same moment. And that's your cluster key. And that basically sorts everything into separate event histories and maintains events timestamp ordering on them. So Cassandra gives you a nice distributed, very highly performant way of performing that kind of sorting and ordering of the events as you perceive them. So one way we might have this set up is that as events come into our event processor, we log them into Cassandra as our event store, and then we also push them out to, say, a RabbitMQ topic for downstream processing somewhere else. And this is one pattern we've actually used in production. The idea is basically things happen, we record them, but also there are other downstream processors that might be interested in those events, and we use RabbitMQ to distribute them out to other listeners. A couple of issues here. One is that obviously any downstream processing is still going to receive the events out of order unless we do some kind of windowing and ordering on them before we push them out to the topic. However, when we go to query events from the event store, we'll get them in the correct order, and then we can play them into our state machine, and so we can query for the current state of any given aggregate, which is very handy. An alternative model which we've been investigating is using Kafka, where the idea is that as events come in, we publish them into a Kafka topic, which gives us durability. We know once they're on Kafka that they'll stick around for a while. And then separately, we have an event store listener that logs them into Cassandra and other downstream processing. So basically, from the point of view of the event processor, once something's written into the Kafka topic, we're done, and we can go on processing other things. And actually, putting things in an event store for querying is one of several tasks that you might run off the Kafka queues. And that seems like potentially quite a powerful approach. So just to summarize the processing model, our events arrive partitioned into leaves out of order, basically kind of fairly jumbled up. We sort them into event histories by aggregate type and ID. We sort them within their event histories by event timestamp and not by processing timestamp. This does create a slight complication, which is that event consumers need to take into account the possibility that an event history might be incomplete at the time it is read. So because things can arrive out of order, we have an image of what's true at a particular time, but then we might receive an event afterwards which actually refers to something that happened in the past. So we may have to accept that our view of the world is not complete and that we might receive new data that changes history. And one way to deal with this is to use something like a watermark to say, okay, there's a given amount of time within which we expect data to have arrived, and that allows us to give incoming events time to settle. There are other techniques as well for dealing with things that arrive horribly late or out of order, and so at some point you have to start looking into kind of ways to incorporate corrections to your data after the fact. So that's a kind of an aspect that you need to take into account. Okay. We'll go on to the programming model. So the core metaphor in the programming model is the consumer of events, which in Java 8 is an actual interface, consumer of event. If I want to emit an event, you give me a consumer of event, and I send events to it one at a time. So here's my event consumer I've been passed in. I create a new event for a particular aggregate ID, particular time, particular name of the event. This business here is just a way of creating the parameters associated with the event in a type-safe way. So a light bulb created schema just says if it's a created event, it'll have a wattage, which will be an integer. And this, again, is a sort of type-safe key that we can use to set that value. So this is a way of creating a sort of type-safe collection of values. Once we've built it up, we just pass it to the event consumer by calling the accept method on it. So consumer in Java 8 is a functional interface, which means it has only one method, which means that you can write them as lambda expressions. So the accept method is just what the lambda calls. So to handle events, we create a consumer of events, we implement the interface, and we handle events that are sent to us. So our consumer of events wattage printer, something that will just print out the wattage of an event. So an event comes in, and we grab the wattage from its parameters and just write that out to the console. And then we can pass our wattage printer into write events, which will write events into it. So most of the interesting stuff then in any kind of event-based system is event handling middleware, which is a chain of consumers of event that transform, route, persist, and dispatch events. So a single event submitted to this chain, we call accept on the consumer of events, might be serialized to JSON, written to a message queue topic, pulled off that topic and deserialized, persisted to an event store, published to an event handler which maintains a query-optimized view of part of the system, published to another event handler which maintains an index of aggregates by event property values. So we see created events with wattage values, and we say, oh, right, this aggregate ID we can associate with 60 watts. So find me all the 60-watt light bulbs. We maintain an index for that. And from the point of view of the caller, all we do is we push an event into the system. We don't know what this processing chain looks like, but we can build an event processing system by chaining these different parts together. Now, in Java 8, we have a mapping layer, which makes it slightly easier to create and dispatch events. So we can define all of the events for a light bulb within a single Java interface and a couple of annotations. So we annotate it to say what kind of thing it handles events for. Light bulb is the aggregate type. And then for each possible event type, we have a method. And by convention, the method has the timestamp and the aggregate ID as the first two parameters, and then any other parameters are just the remaining parameters of the method. And that allows us to define, if you like, the entire protocol for light bulbs. These are all of the events that we might want to create or handle for a light bulb. And that makes it a lot easier to create events because we get an event-emitting proxy, which is just an object that implements a given event interface. And when we call one of the methods on the proxy, it creates the event based on the method parameters and passes it on to this event consumer. So we now have a nice, fairly clean type-safe method of emitting events through this proxy. Equally, if we want to handle events, we can either use the interface we already created, or if we want to handle just one type of event, we can create a little single method interface like created events here. And then we get a dispatcher that will say, when you give me an event, I will convert it into a method call on this class. So I will convert it to a call on the created method in this case. And that's actually then passed through to this lambda here, which takes the timestamp, the ID, and the wattage, and prints it out to the console. So we've got ways to map things from method calls to events, and from events back into method calls, which makes for a fairly tidy programming model without having to create hundreds of POJOs, which is the main thing I wanted to avoid with this. Most other kind of CQRS frameworks basically have a kind of POJO per event type model, which I find hideous. When we want to query events and replay them, we have a thing called an event source. And we can say that we want something that will read events from a particular event source and dispatch them to a particular interface. We ask it to replay the events for a particular aggregate. And then it goes to the event store, it finds all of the events for that aggregate. We can ask it to do this in a particular order or to filter things in certain ways, and then it'll replay them to our handler. And that's our kind of standard querying model. If we want to get a value back out, like for instance we actually want to find out what the wattage of a particular light bulb is, one of the things we can do is use the collect methods, where we pass in a caller, and then we have our lambda that receives the method call. And as a way of passing a result back out, we then give that to the caller. And that's a slightly kind of functional origami, sort of inside-out way of doing things. But it's once you get used to it, it's a reasonably effective way of plucking a particular value out of an event or series of events. Now, we don't have to use that particular mapping. We could have a Java mapping that actually did turn things into POJOs. Kotlin, it turns out, has got quite a nice model for this. So in Kotlin, you can have a sealed class, which is a class that can only be extended by classes declared within its own boundaries. And so this allows us to we can define our events as subclasses of a sealed class. Here we go, created, screwed in, unscrewed, switched on, switched off. And they're all instances of light bulb events. within the constructor for each class, then we can have the parameters for that event type. So it's about as concise as the interface approach, but now we actually do have one class per event type. And once we've got that, we can write out events. We've got a thing called an event bus, which allows us to gather up a collection of events to be processed together. And the nice thing here is that the timestamp and the ID no longer have to be part of the events data. So each of these things is defined just with its parameters, and we have a kind of a generic approach to emitting events. So we emit created, screwed in, switched on, and so on. And then we can use Kotlin's pattern matching. So we get a whole bunch of events replayed from our event source, and we say, for our event, look at the events data, and when it's this kind of thing, return this. When it's this kind of thing, return this. So it's very much like pattern matching in Scala. And that gives us a really concise way of handling multiple different kinds of events in a single expression. The other nice thing about sealed classes is that it knows whether or not you've handled every possible case, and the compiler will complain if you miss one out. How long have I got? 10 minutes, great. So the state diagram, in Java it's kind of difficult to really model state processing because what we really want to do is have immutable objects and play a stream of events and sort of create copies of immutable objects to build up the state history. It's a bit ugly in Java. It's a lot less ugly in Kotlin. So I'm going to just talk through very quickly how this works. The basic idea is that we have an update method which accepts maybe a previous state if we've got one, or we might be starting from the null case where there isn't any state yet. So the question mark means it's nullable. We might have a previous state or we might not. And it receives an event. And then it may or may not return a state. So if you have no state and you have an event that is not a kind of creator of an object, then you still have no state. If you have no state and you have an event that is a creator of an object, obviously you get a new state. And so that's our logic. We look at our previous state. If we don't have a previous state, then we try to map an initial event, passing the event through. Otherwise, we call next to apply the event to our previous state and get a new state. So anything that implements transitions has to implement a function that might create a new state from an initial event, or that can update an existing state from a new event. And then we've got a run all method where you give it a list of events. You might give it an initial state if you've already got some information. And it will just run through, it's got a working state, and it just runs through the events and applies them repeatedly to the update. So that allows us to run a sequence of events to a state model. So here we have instances of that for the light bulb. The initial handler just says if it's created, you get a new light bulb state. We initialize light bulb state with the wattage. There's no other information yet. If it's not created, we return null. We don't know what to do with any event that isn't created when we're looking for an initial event. In the next method, we've got our previous state and we've got our new event. And we say, okay, what is it? If it's created, doesn't make sense. We stay with our previous state. If it's screwed in, we take our previous state, but we make a copy of it, updating the location to be the location that we were given in the event. If it's unscrewed, we take our state and we make a copy of it, setting the location to null. And there's various other rules for managing the state transitions. So we can kind of model the entire state diagram programmatically in quite an intuitive way. So to summarize the programming model, you have the event type and middleware which implements consumer of event provide the basic mechanics for creating, processing and handling events. The Java 8 mappings provide a convenient and type-safe method mapping wrapper around these mechanisms. The Kotlin mappings provide an alternative wrapper based on immutable classes. And other mappings are possible. You could do a Scala version, you could do a closure version, you could do Java with POJOs if you liked. So the core of the system is the event type. which allows us to kind of move events data around in a generic way. And then the mapping layer is a way to kind of make that more usable within whatever language or paradigm you want to use. Okay, that's pretty much it. There's a homepage for the project, which has links to some blog posts on the implementation and a fairly long technical report that myself and Tarek wrote. It's open source, and the source code is all on GitHub. And yeah, pull requests are very welcome, or bug reports. Okay, thank you very much. Mm-hmm. It's pretty much horizontal because we're basically partitioning everything that comes in into an event history for whatever the thing was, and so the picture I have of the data is a very large number of fairly shallow buckets. And basically, as data comes in, we fill up lots and lots of buckets. And that works well with a kind of clustered key value store like Cassandra, because Cassandra's very good at having lots and lots and lots of buckets. And generally, it's better if you don't have any one bucket that's kind of much fuller than the others. If you have a kind of disparity where maybe some kinds of things have very, very long event histories and others have shorter event histories, you might want to start thinking about kind of treating them separately or storing them separately. So the model that we have just kind of assumes more or less uniformity of depth of event history and of kinds of things. Also, I guess one of our working assumptions has been that things don't last forever. That you might, you may be able to dispose of or archive or kind of provide a snapshot summary of the state of older things, because otherwise it's an append-only model and things grow indefinitely. So you do at some point have to think about, over the entire lifetime of our business, are we going to generate more data than we can reasonably handle? Do we really care about the entire event history of something 3 years ago, or can we just archive a snapshot of its final state? One of the reasons why it's useful to identify terminal events is that you can say once those have occurred, nothing else is going to happen to this thing, and that provides you with a basis for implementing policies for clearing things away and archiving them. Mm-hmm. So the question is about relationships between things that actually very often are things are related to other things, possibly in a kind of a hierarchy. There are light bulbs inside houses, there are manufacturers that produce light bulbs and so on. And in this model, really, we don't have any concept of relationship. We just have a collection of buckets. And so the answer is that you model your relationships externally. You reason about things and about their relationships in your downstream processing. So a phrase that I've used to describe this is write first, reason later. We capture our events histories, we write them into Cassandra, we're able to query them. We're also able to feed them into things like Spark streaming and process them in order to extract patterns of relationship and more complicated models. Or, again, in the slide we had earlier, roll back quite a bit. So we're logging events in this one format, which really only contains the history of what happened, but we're also pushing them out to downstream processing where we might build particular views of entities. Typically, when we're interested in relationships, we're interested in current state. We're interested in the picture of the world as it is now, and then how this thing is related to that within that picture. So we've got kind of two different dimensions. We've got our kind of historical dimension, everything that happened, and then we have our kind of current state where we very much are interested in looking at relationships between things and being able to traverse through them. And so at this point, you might build up a model in a relational database and a graph database. You might actually have multiple query optimized views that enable you to interrogate your current view of the system to find out how things relate to one another and to be able to search and traverse from one thing to another. You can't do it with this Cassandra data model by itself, but you can do it by pushing the data from this out through Spark, for example, which then gives you access to a much wider range of ways of kind of slicing and dicing and combining information.
Thank you very much, Tom.
Thank you very much.